Good morning, YouTubers. And we're going to continue working on this problem of mechanical engineering, particularly this one pertaining to static uh, analysis. And here we have a bar, so it looks like a crowbar or something. And that bar is being pulled here with a force of 400 Newton. And the bar has a pin here as per this design, and it's also have a connection here. So you are pulling here, and basically let's do the first thing that it asks is connected to short link as shown. If the weight of the member is negligible, determine the force of the pin on lever A right here. So we have a bar, looks like this. Let me draw something similar, and there's a force here of 400 Newton. Divide by 10, that would be about 40 kilograms, multiplied by 2, about 80, a little bit more of 80 pounds force here. And there's a pin here, and as we know, pin will not carry any moment, so there's only two forces that we need to worry about, which will be a force here. Let's call that force FAX, FAY, and here FAX. There's another pin here, and that pin, if we are only drawing this bar here, also we have some forces. Typically I like to draw this, like they are getting into the pin. We know that this does not make too much sense, but you get used to it. And what I'm saying is that this force here will be, this pin is called B, so that's gonna be BX, and this is gonna be FBY. Now, here's the story. We have four unknowns, and the problem with that, of having four unknowns, is that we definitely have one equation that has to do with moment around A, and you can take whatever direction you want, like for example positive, this direction must be equal 0 given that there's no moment here, and with respect to a pin. But then you have another equation, is that the sum of the force in X will be equal 0. Let's say that this is positive that direction, and the sum of all the forces in Y equals 0, and let's take positive in that direction. If we do that, we have three equations. The problem of that is three equations, four unknowns. This will not work at all. That's the problem. There's no magic here. And the problem is that if you check only on this bar, on the free body diagram, you are missing something, which is very important, which is basically the direction of this force. I need to know what's going on here on that pin. So, and that will come from the other part here, other piece. So let's say they draw this piece here, and it says as 0.2 up and 0.2 on length. Let's draw that second part here. So we have a piece like this, and let's draw like this, and there is a pin here and a pin here. So we know that these forces on this pin, let's say that I draw a force, I don't know, like looking like this at a certain angle. That force will be decomposed in a force like this and another force like this, right? So this is the main force at that pin. But then what's going to happen is that this pin here will see those forces, and to cancel them out, then you will have to have a force like this one against this one on the X direction, but this force here has to go down, meaning that this force here is like you are doing like this, right? So it will be transferred from this pin to this pin to make this static, so that it will not move. Now, what's the story here? The story is that by doing that, then you have the angle. What is the angle of this, right? So for this problem, this is 0.2, and this is 0.2. So you can establish, like for example, what is this angle here? Very straightforward. to carry that angle. That angle will be like, for example, if you take this as 0.2 here, and basically this is 0.2, so they are the same. You can have theta, which is this is theta, is equal to 0.2 over 0.2. So theta equal the inverse of the tangent. This will be 1. Let's write 1. So theta in this case is obviously 45 degrees. But you can imagine that this piece here could be very different. Like, you can draw any piece. Like, for example, let's say that I draw a piece like this. And this piece is connected here. Again, by the same argument that I just did, you can have, like, for example, a force here, somehow like this, and this is coming down, and this is coming this way. But then this force will be transferred to this pin here as well. So so you have a force against this one and a force against this one for equilibrium. And then what we need to do is to find what's the angle of this force with respect maybe to the horizontal. So you want to find this angle here. So in essence, you have this distance, whatever is here. Let's say that here is 0.2, and that this distance here from here is 0.6, right? So you have from here to here 0.6. So, and here is 0.2. So this angle is again will be theta. For this angle will be the inverse of the tan, and that would be 0.2 divided by 0.6, and that theta will be, in that particular case, that theta will be in that case 18.43 degrees. So what I'm saying is that although you can work the free body diagram or the larger body here, but still you need somehow what's happening with the second one, not in terms of magnitude of the pin on that particular unit, but at least the direction of the force, what's going on. So with that said, like for example, this is the example that we are working, so we know that the force is doing this. That force is coming right at 45 degrees angle here. See, like this. That's what I'm saying. And what would that do for us? Oh, very straightforward, because now we know that FB can be broken in two parts. One is on this part and on this part, based on that we have more information on the angle of that force, meaning that instead of having two variables here, FBX and FBY, I only have one FB. Now we are talking. Why? Because we have the moment and the moment at A, the sum of the force in X, and the sum of the force in Y. So we have only three variables, which will be FB, FAX, and FAY, and the problem can be solved. Very straightforward. But what we know already, like for example, let's do a moment analysis here on A. So the moment analysis on A, let's say positive that way, will be, if you do the moment, you take the moment right here, then these two forces are gone, so you only end up having FB, and FB will be broken, like for example, on a force coming that way, and according to the problem, that elevation is about 0.2 from here to here for that moment. And then I have another force that is the decomposition of FB on the Y direction, and that distance is about 0.2. So we are ready now to take the moment around point A. This point is called point A, and let me check the dimension again. And from here to here 0.2, and from here to here 0. Got this bad. Let me fix this. 0.1. There we go. Now the moment at A, like this, positive direction, that would be 400. That would be 400 times the total distance, and this got deleted, 0.5 and 0.2, that's 0.7, going on the positive direction of my moment around A. How about this force here? That force is FB plus FB times the decomposition of B on the X, so that would be cosine of 45 times the elevation, that's 0.2. But then what else I have? I have this guy, and this is 0. Wow, this looks bad here. The distance from here to here is 0.1. See right there, plus FB, and that would be FBY. The decomposition would be FBY. That would be sine of 45. Not that we care much about sine and cosine because it's 45 degrees. It's just I want to be sure that you use the right, that you use whether it's cosine or sine right. Otherwise, it's gonna get crazy. Now, that would be that distance from A. That would be 0.1. And now, anything else that would be equal 0. I don't have anything. That the moment on A and pit A, that would be that moment equals 0. Now all are positive. That means that definitely the direction of the FB must be wrong, because I have that direction going like this, going up on that pin. Anyway, that will be fixed in a second. So the result here will be FB will be cosine of 45. I use the distributed here, plus sine of 45 times 0.1, and that is equal minus 400 times 0.7. So the result of FB will be negative, and let's pull the calculator here. Negative, that would be 400 times 0.7, that's 280, minus 280 divided by the sum of these two guys, that would be cosine of 45 times 0.2 plus sine of 45 times 0.1. That sum is 0.21213. So you end up with about 1,320 Newton, or 1.32 kilo Newton. So that's FB. So that's this force here, but that's negative, meaning that the right direction of FB to be positive 1.32 kilonewton is like this. So instead of going this is wrong, it's going that direction, meaning that this is wrong. It's going this direction, meaning that this is wrong. It's going down. Now I got that right. So the next part is find. The question here was, what is the force at pin level A? So I need to find out what is FAX and FAY. So for that, the sum of the force in X, that way positive equals 0. So what we got here, the 400 is going where I wanted. So it's 400. What else we have? This force I already fixed the direction, meaning that's going in the toward your left, not to the right. So that would be minus FB, but I know FB is 1.32 times, and that force is on the cosine of 45. Not that we care much about sine and cosine of 45 because they are the same, but be careful, you know, it's going the x direction, the degrees is this one, so you are talking this direction here, so that would be cosine of 45 going that direction. Now fax, I also have it pointing toward the left, meaning that's minus fax equals 0. So let's do the calc, and remember this is 1.32 kilonewton, and we have to be careful not to mix unit here because this is Newton, so that means is minus 1320. That would be better. Newton, and this is Newton now we are talking about, and this is cosine of 45, and that looks good. So finally fax equal, this go this way, so end up being 400 minus 1320 times the cosine of 45, and let's see where we are. fax equal negative 533.4 Newton, meaning that my direction of fax is wrong, so that means positive 533.4 Newton, but it's going sorry, not that direction. Remember fax, I assume that it's this direction going that way, but that end up being negative, so the direction, the right direction is that way. That's the positive direction for fax. Now what happened with fay? That the sum of the forces in y equals 0, meaning that, let's see what we have in the y. The y, this is coming down, positive going up, meaning that negative of the force coming down, that would be 1320 times the sine of 45. The only thing going up is fay plus fay equals 0. So the only one that I got the direction right is fay equal 1320 times the sine of 45. So we end up fay equal positive 933.4 Newton. So I got that the composition of the force at the pin A, fax, and fay, and the only fay the direction got right. So what's the magnitude at pin A will be then the square of fax as 533.4 plus fay 933.4 square, the square root of all that. So the magnitude at pin A is, let's see what we got here, square root of and the result is about 1075 Newton, and or 1.075 Newton, kilonewton. So this is the result, and the angle of that one in particular, let's get the angle. The angle will be theta will be the inverse of the tangent of, let's see what we got here, fay is 933 and fax is 533. So theta, let's see what we got, 933 933.4 533.4, that's about 60.3 degrees, meaning that if I want to locate that force, right, well, I can use here or here, that force is somehow looks like this, and that the angle here is about 60.3. That's it. So here is 60.3 degrees. That is decomposed in this force FAY and in this force FAX. Well, that kind of summarizes everything. The most important part here is that without having the proper direction of what is FB here, I was unable only to use by using only this member. I was totally unable to resolve the problem because I have more unknowns that equation that I have possible. Remember, I only had these three equations to solve any problem. If I have more unknowns that equation, there's a problem. So we end up using the bar here just to find out that that force definitely got across through these 2 points here, one way or another, which in this case end up being like this, right? A line like this. And that line provide then, based on the distances here, provide the proper angle of where that force is directed to. Well, folks, that's more than enough. I think we beat this horse good enough. Well, folks, that's basically it. Have a great day, whatever be your final destination. Bye.